For this lesson, we are going to look at an example of how we can use all of the calculus stuff we have done so far to sketch a curve. This lesson will cover a polynomial curve. The next lesson we'll look at asymptotes and how to sketch rational functions or anything that might have an asymptote. So we are going to sketch f of x equals 2x cubed minus 12x squared. And so in order to do this, we are going to be going a bit deeper. So the very first thing we want to look at is we want to look at what the domain and range are. So what are the domain and ranges in which we're interested in examining this function? So this is a polynomial, so the domain, x is all real numbers. It's a cubic polynomial, so that means that y is also an element of all real numbers. There's no maximum or minimum value. Okay, and we know that there's not going to be, if you have an even degree polynomial, you will have some maximum or minimum value, depending on which one. Odd degree polynomials don't have a maximum or minimum value. Okay, next we are going to look at the zeros or x-intercepts, and these are we can use our pre-calc 12 techniques to solve these. We can use our rational root theorem, or we can factor if possible. So generally, either you will be given the equation in a form where you can find these zeros or x-intercepts, or you don't necessarily need to calculate them exactly. So if you have certain points that are above, certain points that are below, you can estimate them, but generally you'll be given functions where it's possible for you to calculate the x-intercepts. So f of x, we're going to try to factor this. So we can factor out a 2 and we can factor out an x squared. So that leaves us with x minus 6. So we have two roots. The 2x squared gives us x equals 0 as a root. And the x minus 6 gives us x equals 6 as a root. Okay, so that means we have two coordinate points. So we have 0, 0. And we have 6, 0 as x-intercepts. And the y-intercept. So none of this is any different from how we've been sketching curves in pre-calc 12. So domain range, zeros, x-intercepts, y-intercept. Okay, so our y-intercept, we're going to plug in f, we're going to find f of 0, which is equal to 0. So our y-intercept is the same as our x-intercept, which is 0, 0. Okay, so entering the calculus stuff, the next thing we're going to look for is critical points. So generally, the way we're organizing this is we're looking at things that involve the function, f of x. Now we're going to look at what we can discover by using the derivative, f prime of x. So we're looking at f prime of x equals 0, gives us critical points. We also want to know where f prime of x does not exist. So let's find our derivative. Okay, those will both give us potential critical points. Okay, so f prime of x is equal to, let's go to our original function, we get 6x squared minus 24x. If you want to just, we can refer back up, we had 2x cubed minus 12x squared, so the derivative is 6x squared minus 24x. Okay, so we're going to plug in this equals 0. Okay, this is a quadratic function, so it exists everywhere. We don't need to worry about any does not exist points. So we have 6x times x minus 4. So it looks like we have a critical point at x equals 0 and at x equals 4. And now we want to also find the y values of these points. So 0, if we plug in 0, we know the y value is 0 because that's also our y-intercept. And we calculated the x-intercept here. Now we're going to plug in 4, not to our derivative equation, but we are going to plug it into our original equation. So 2 times 4 cubed, 4 cubed is 64, 2 times 64 is 128. 128 minus 12 times 16, we wind up with negative 64 for our y value. Okay, so please do remember we find This is f of 0, not f prime of 0, and this is f of 4, not f prime of 4, because we know f prime of 4 and f prime of 0 would be 0. Okay? So just remembering we have to refer back to the function to find y coordinates, and that happens for everything. So when we look for our inflection points, that's also going to be where we find those inflection points. Okay? So we found our critical points. That's to do with the derivatives. We haven't yet determined the nature of the roots, and we're going to do a sketch. So we could now use the second derivative test as we go on to take the second derivative, but we don't need to because we are going to do a sketch anyway because we're doing this curve sketch. So let's look now for our inflection points. That will tell us where we are potentially changing our concavity, which is when f double prime of x equals 0. So let's find f double prime of x, which is equal our second derivative. So that is 12x minus 24. So if we plug in 0 equals 12 times x minus 2, so x is equal to 2 to make that 0. Okay, and again, we want to find our y coordinate because we are eventually going to be sketching this graph. So I'm going to plug 2 into f of x. So 2 times 2 cubed is 2 to the 4th, which is 16, and 16 minus 12 times 4, 12 times 4 is 48, 16 minus 48 is negative 32. So that's 2, negative 32. And remember, this again is f of 2, not f prime of 2, not f double prime of 2. We just go back to the original function to find y values. Okay, so now what we're going to do is we're going to draw a graph, and we're going to put any of the important points. So we've discovered critical points, we've discovered inflection points. We could put the zeros in here as well, but we're going to find that doesn't matter as much when we're trying to figure out what the graph looks like. So I actually usually don't put the zeros into my sketch, my little sketch chart, because I don't want to have too much information or enough that it's confusing. So I'm going to put f prime of x, f double prime of x, and then we're going to do a sketch. And the points I'm going to put in here, I'm going to put 0 for x, because that was one of my critical points. The next important point was 2, which was my potential point of inflection, and then 4 was another one of my critical point. So this is a critical point here, and this is a point of inflection. And generally you want to put any of those into your little chart. And then we're going to look at where each of these is positive and negative. And you can pick a test point to figure out whether it's going to be positive or negative there. So jumping right in. And generally when I'm doing these, especially in my head, I do like to. So remember, f prime of x, I'll just write it in brackets under here, is 6x times x minus 4, and f double prime of x is 12 times x minus 2. It's just sometimes a little easier to see whether that's positive or negative. So when we're less than 0, if we take negative 1 times 6 is negative, negative 1 minus 4 is also negative. A negative times a negative is going to be a positive. So f prime of x is positive. At the critical point, it's 0. At the other critical point, it's 0. Between 0 and 2, I try 1. 6 times 1 is positive. 1 minus 4 is negative. A negative times a positive is negative. Similarly with 3, 6 times 3 is positive. 3 minus 4 is negative, so negative times a positive is still negative. And then greater than 4, 6 times 5, 5 minus 4, positive times a positive is positive. F double prime of x, we have 12 times x minus 2. So when we're smaller than 0, x minus 2 is clearly negative. When we are between 0 and 2, x minus 2 is still negative. 12 is going to be positive no matter what. When we become greater than 2, it starts to be positive. Okay, and here at 2, it's equal to 0. That's going to be where it changes. Okay, so now we have to interpret this. So let's look at what each of these means. So f prime of x plus means we have an increasing function. Okay, so let's even just, so f prime of x, if it's plus, we have increasing. So we're going up minus decreasing. F double prime of x, if it's plus, we have concave up, and minus, we have concave down. Okay, so now we're going to interpret this in light of, we're going to look at these both together in order to draw our sketch of f of x. Okay, so this is what f of x is doing based on what's happening with the derivative and the second derivative. So here in our first region, less than 0, our derivative is positive, so that means we're increasing, and f double prime is negative, which means we're concave down. So for a sketch, up and concave down, increasing and concave down looks like that. Okay, we have our critical point. We calculated that was 0, 0. And on the other side, we have a negative, so we're decreasing, but we're still concave down. So that looks like that. So that's what that little sketch looks like. So this means that we have a local maximum at 0, 0. So now we have a point of inflection, which means we're going to potentially be switching concavity. On the other side of our point of inflection too, we are still, f prime of x is still negative, so we're still decreasing, but this time we are concave up. So decreasing and concave up looks like that. So we have now a 0 at 4. We had 4 comma negative 64. And on the other side, we are increasing in concave up, which will look like that, which makes this a minimum value at 4, negative 64. Okay, and this point right here we know is at 2 comma negative 32. Okay, so now we have enough information. We can see we start concave down, and that is anything less than 0. We are going to our point 2 comma negative 32. That where we switch concavity, and then we're going to a minimum at 4 comma negative 64. So now we are going to draw a nice detailed sort of graph here. Okay, so we are going to go right here, and I'm going to use the information that I have here to kind of notice that I'm going to want a little bit more maybe below the x-axis than I need above. And I'm also going to scale like negative 30 and negative 60 because I want to be able to fit everything on here because I know I'm going to have to reach a minimum at 4 comma negative 64. Okay. So now I'm going to go, I know my points I'm going up through about, I had a, and this is where I actually do want to kind of refer back to my x-intercepts. So way back up here I had x-intercept at 0 comma 6, and the 6 is sort of the furthest out point where there's anything really happening. So I'm just going to make my graph go 1, 2, 3, 4, 5, and 6. And then whatever happens beyond there I'm not as concerned about. Okay, so I'm just going to go left to right. First thing I have happening, and sometimes it can be nice to kind of zoom out. So first thing I have happening, and you might want to just transpose down here, x-intercepts 0, 0, 6, 0. Okay, so I can just throw in my x-intercepts because I know I'm going to have to pass through those points. I am going to throw in my point of inflection, which is here at 2 comma negative 32, so just a little below negative 30. I've got my 4 comma negative 64 for my local maximum, which is maybe even a little closer to being at negative 60. That 4 won't be super noticeable. And then I've got my other x-intercept. That could probably be a little over to be a 4. Yeah. Okay. So now I'm going to sketch my graph using my important points. So I'm going to go up to here. Okay, we have a local maximum at 0, 0. So at 0, 0, I'm actually going to turn back around, and I might even level this out because we're using such a steep scale. It's possible that this will look a little bit more level in that steep scale. If you want, anytime you want a little more accuracy in a region, I'm mostly going to be looking for your calculus pieces, do you have those pieces accurate as well as your x-intercepts? But if you ever want to sort of zoom in on a section of your graph and you say, well, I don't know quite what's happening at -1, just plug in -1 into f of x and see what the y value is, and that'll give you an idea of how steeply your graph is moving. So here, we're going to go down, and we are going to be concave down when I'm sketching my graph. So I'm making sure I get that nice concave down shape as I'm sketching. I'd use pencil for this in general, until I get to my point of inflection. Okay, so I have my 0, 0, local max. I get down here to +2, -32, which is my point of inflection. Then I'm going to switch concavity. So now from to -32, I'm going to be concave up until I hit 4, -64. So this is 4, -64, and that is a local max, local minimum. And then I'm going to turn back around and I'm going to continue to be concave up for the remainder of my graph. And the concavity isn't going to switch back. It's not going to turn around again and start becoming concave down. Okay, so concavity is the same. And now I have a lovely and relatively accurate sketch of a curve with my minimums, maximums, and points of inflections in exactly the right place. Thank you, calculus.